Welcome to Unit 3 review. This unit will focus heavily on intermolecular forces, or interactions between molecules.
Specifically, we will discuss the types of intermolecular forces, properties of solids, the phases of matter, the ideal gas laws and kinetic molecular theory, as well as important deviations, followed by solutions, their representations, separation techniques, and solubility. Then we will finish with spectroscopy, the photoelectric effect, and the Beer-Lambert law.
Since so much of what we will talk about will rely on an understanding of intermolecular forces, let's start out by listing the types that are possible and defining them.
First, we have ion-ion interactions. Large ionic solids are held together by these networks of ionic bonds, which are the strongest intermolecular force because they involve formal charges. These are essentially just the ionic bonds we already learned about, simply applied on a larger scale. So let's quickly move on to the next intermolecular force. Next, we have ion-dipole interactions. So first we must recall what a dipole is. The covalent bonds in a water molecule are polar because oxygen is more electronegative than hydrogen and will pull the electrons in the bond towards itself. Because of the bent shape of the molecule, when we combine these vectors, we see that water has an overall dipole, or a side of the molecule with some electron excess and a side with electron deficiency. Dipoles can make electrostatic interactions because the partially negative side is attracted to positive charges and the partially positive side is attracted to negative charges. So when sodium chloride dissolves in water, the sodium ions make ion-dipole interactions with the negative side of water's dipole, and the chloride ions make ion-dipole interactions with the positive side of water's dipole. Each ion can make several of these interactions, which are very energetically favorable, and this is why sodium chloride will dissociate in water in the first place. Next, we have dipole-dipole interactions. As you can guess, this is when dipoles interact with each other, as with pure water. When in liquid form, water molecules will move in such a way so as to always be making electrostatic interactions between the negative end of one dipole and the positive end of another dipole. In this case, these dipole-dipole interactions qualify for a special title, hydrogen bonds. This is when dipoles generated by NH, OH, or FH bonds interact with each other. These are especially strong because these are the most electronegative elements, so they will create the most strongly polarized bonds, resulting in a very strong interaction. We can almost think of partial charges as some fraction of a formal charge. So the greater the partial charge, the stronger the interaction, though never quite as strong as interactions between formally charged particles. Lastly, we have London dispersion, often just called dispersion interactions. This is the consolation prize of the intermolecular forces because any substance can do it. Only ions make ion-ion interactions, and only covalent molecules with a dipole can make dipole-dipole interactions, but absolutely anything can make dispersion interactions. For example, take a look at helium. Helium is a noble gas, and due to a full valence shell, it does not make bonds with other atoms, so a sample of helium is just a bunch of helium atoms. While the electron cloud around a helium atom will at any time be slightly skewed in one direction. This will result in something called a momentary dipole. This means one side of the atom is ever so slightly partially negative, and the other side is slightly partially positive. This is dramatically weaker than a formal dipole, but it still exists and can be measured. If this momentary dipole approaches another helium atom, it can generate an induced dipole, meaning the slight partial negativity repels this electron density over to the other side of the atom, so that it will also have a slight dipole. And then there can be a momentary dipole-induced dipole interaction that is described as a dispersion interaction. This is a weak and fleeting attraction, but this is all that monoatomic species and nonpolar covalent compounds can do, and for very large molecules like some hydrocarbons, the force can become significant. To summarize, ion-ion interactions are the strongest because they involve interactions between formally charged particles. Ion dipole is next because it involves a formal charge and a partial charge. Then dipole-dipole, which is between two partial charges, and finally dispersion interactions, which happen between tiny induced dipoles. The types of intermolecular forces that occur within a substance can determine many physical properties. One such thing is the phase that a substance will be in at a particular temperature, and the temperatures at which phase changes will occur. Let's take a look at exactly how this works. The three phases of matter we are most familiar with are solid, liquid, and gas. Every substance exhibits some kind of electrostatic interaction between its molecules, even if only dispersion interactions. The stronger these attractive forces, the more the molecules stick together, and will thus be a liquid or even a solid at higher temperatures. That's because particles in a solid or liquid are close together, essentially touching, and thus participating in interactions. In a gas, the particles are far apart and not interacting, so the stronger the attraction between the particles, the more heat energy that will need to be provided in order to overcome these attractions and put the substance into the gas phase. If more heat energy is required, this translates into a higher boiling point. Raising the temperature means adding more heat energy, which means generating more kinetic energy for the particles, which eventually results in vaporization at some temperature that depends on the identity of the particles. We are now equipped to look at every phase change in this kind of lens by considering the ways the molecules are interacting with each other in the context of available heat energy. Take water, for example. When water vapor in the atmosphere cools, it will condense, which we might see in the form of dew on a leaf. This is because as they cool, the molecules travel more slowly, which makes it more feasible for them to attract one another through intermolecular forces and begin to stick together. Water will boil, freeze, and melt for similar reasons. The change in temperature results in a change in kinetic energy, which makes the molecules either stick together more efficiently or less efficiently. Solids maximize intermolecular attractions because the particles are not moving, so they are locked in a lattice that will obey a geometry that allows it to exist at the lowest energy possible. Liquids exhibit intermolecular forces as well, but the particles are constantly in motion, so these interactions are fleeting and ever-changing. And a gas will not exhibit these forces, as the particles are too far away from one another to interact. Let's use some quantitative data to compare interactions. We know that dipole-dipole interactions are much stronger than dispersion forces because formal dipoles are so much stronger than the temporary induced ones, so they generate stronger electrostatic interactions. We can see precisely how much stronger these dipole-dipole attractions are if we consider a few specific molecules. Compare hydrogen chloride with molecular fluorine. These are both diatomic and have roughly the same mass, so we could expect them to have similar boiling points. However, at 150 Kelvin, hydrogen chloride is a liquid and fluorine is a gas. This discrepancy is due to the dipole-dipole interactions that hydrogen chloride can participate in, which fluorine cannot, because fluorine is strictly nonpolar, while HCl contains one polar bond and thus a net dipole. The presence of these stronger dipole-dipole interactions between HCl molecules means that the molecules stick together better and remain liquid at higher temperatures. So when we look at molecules, it is important to be able to tell whether the molecule is polar overall, that is, whether it has a net dipole, because if it has a dipole, it can participate in dipole-dipole interactions, which will dramatically impact key characteristics of that substance. If a molecule is completely nonpolar, it will only be able to participate in dispersion forces, which typically means lower melting and boiling points. So when comparing two substances and making a prediction about boiling points, we must examine two things. First, which is the strongest type of interaction each substance is capable of? If one makes hydrogen bonds and the other makes only dispersion interactions, unless the second is dramatically more massive than the first is much more likely to boil much higher, since hydrogen bonds are so strong. If instead the two substances make the same strongest type of interaction, we have to see how well they do it. Take the noble gases, for example. These are monoatomic species. Which will boil the highest? Well, the larger the atom, the larger the surrounding electron cloud, and the more significant the momentary dipole that can be produced. So the larger the atom, the stronger the dispersion interaction, and the largest noble gas will therefore boil the highest, while helium, being so tiny, has the lowest boiling point of any substance in the universe, boiling at barely above absolute zero. With melting point, things are a bit different, as we are moving between two phases that both involve particles interacting with each other. For this reason, we examine how well they fit into a lattice. Molecules that are compact, with low surface area, fit very well into a lattice and can maximize electrostatic interactions. These will be harder to melt, and thus melt higher. Those with greater surface area will have difficulty fitting into a lattice and will thus melt at a lower temperature. This is easiest to see with hydrocarbons that have the same mass but different connectivity. The more branching there is, the more compact it becomes, and it will thus melt higher. The more linear it is, the more it will snake around and have difficulty fitting into a lattice, so it will make weaker interactions and melt at a lower temperature.
With intermolecular forces and phase changes understood, let's look at each phase individually and expand on some key concepts. First up, solids. This is the phase where particles are essentially not moving with respect to one another.
Let's quickly list the types of solids we may encounter. First, we have crystalline solids. These are solids that have some kind of reliable and repeating structure, and they can be categorized as molecular solids, network solids, ionic solids, and metallic solids. Molecular solids are just the solid phase for small molecules. So when water freezes to form ice, that's a molecular solid, because it's a bunch of tiny water molecules frozen in a particular lattice structure which allows hydrogen bonding to occur. Each molecule retains its own identity and are connected strictly through intermolecular forces. Then with network solids, that would involve covalent bonding throughout the solid. So when carbon forms a diamond, that would be a network solid because covalent bonds connect every single carbon atom in the sample. Ionic solids involve ions that form a particular lattice so as to maximize electrostatic interaction between formally charged particles. This would be something like sodium chloride, with positively charged sodium ions and negatively charged chloride ions in a grid. And metallic solids involve metals, whose atoms form a network just like network solids, except that the metallic bonds that connect them are a little different from regular covalent bonds, due to the way that electrons can delocalize and move freely through the system, allowing for the conduction of electricity. Molecular solids tend to have the lowest melting and boiling points since the intermolecular forces holding the molecules together are relatively weak. Apart from these four types of crystalline solids, we can also have amorphous solids. These do not conform to an organized lattice structure, often because the molecules are very large and do not lend themselves to organization, such as with some polymers and gels.
With solids covered, let's now move on to gases. This is the phase where the particles are in constant motion, with the particles essentially not interacting.
There are certain assumptions we make when looking at gases that simplify things dramatically, and these assumptions are described by something called kinetic molecular theory. This theory is the framework within which we will be describing gases, and when we apply this theory, the gases we describe can be called ideal gases. To understand what we mean by an ideal gas, we will have to examine this theory, which takes the form of 5 postulates, so let's quickly run through them first. Number 1, we make the assumption that a gas is made up of particles, whether they are individual atoms or small molecules, and that these particles are always in motion. Throughout their motion, these particles travel in straight lines unless they collide with something, whether that is another gas particle or the walls of whatever container they are in, at which point they will bounce off and change directions. This vision of gas particles as moving around like billiard balls on a pool table seems pretty intuitive, but it is an important one as it implies that tiny particles like atoms are subject to laws of motion just like macroscopic objects are, and that they won't simply stop in their tracks and change direction without cause. Number 2, we can assume under most sets of conditions that the gas is mostly empty space. This means that the fraction of the total volume that is occupied by the particles of gas themselves is so close to zero that we simply ignore it, regarding them as essentially dimensionless points. This is in stark contrast with solids and liquids, which are non-compressible because all the particles are pretty much right up against one another. There is very little empty space between the particles. Number 3, the phenomenon we refer to as pressure is actually the gas particles in the sample imparting some of their kinetic energy of motion onto the walls of the container every time they collide with it, just like a macroscopic object would transfer energy onto some surface during a collision. It may seem like atoms are so tiny that they can't impart much force, and that's true, but remember that in any sample of gas there are trillions and quadrillions of particles, so altogether it can add up to a lot. If there are a lot of particles moving very fast, there are many collisions, so the system exerts a lot of pressure. If there are very few particles moving very slowly, there are very few collisions, and thus the system exerts very low pressure. Number 4, we ignore the possibility that gas particles could exert any kind of gravitational or electromagnetic influence on one another. Although they technically do interact slightly due to dispersion interactions or even dipole-dipole interactions if the molecules are polar, we consider such interactions to be entirely negligible, so any collision will be treated as purely elastic, or occurring with no loss of kinetic energy. They will simply bounce off one another, once again, like balls on a pool table. And number 5, the average kinetic energy of the particles in the gas is proportional to the temperature of the gas in Kelvin. This means that if you increase the temperature, you increase the kinetic energy, which means the particles will be moving faster. This means that in this specific context, temperature is entirely indicative of average molecular velocity. This relationship is depicted nicely in something called a Maxwell-Boltzmann distribution, where we can see velocities of particles within a gas at a given temperature. As we said, when we are operating within the framework of kinetic molecular theory, any gas that we are examining can be described as an ideal gas. There are a number of laws that apply to ideal gases which allow us to make predictions about the parameters of gaseous systems, and under normal conditions, these predictions are exceedingly accurate. The parameters relevant to these laws will be pressure, volume, moles, and temperature. Again, pressure refers to the force exerted by the particles on their container, so essentially how often the particles hit the sides. Volume refers to how much space the gas fills up. Moles refers to the number of gas particles in the sample. And temperature refers to the average kinetic energy of the particles, or essentially how fast the particles are moving. Now let's see how these relate to one another in specific laws. Let's look at a piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed, if we compress the volume, the pressure must go up. The particles will be hitting the sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional. If one goes down, the other goes up. This is expressed in Boyle's law, P1V1 equals P2V2. If we double one variable, we have to cut the other one in half in order to keep this equation valid. Volume and temperature are also related. If we have gas in a balloon and we heat it up, the particles will move more quickly. In order to keep pressure constant or hit the sides with the same frequency, the volume will have to expand. This means that volume and temperature are directly proportional. If one doubles, the other must double. This is given by Charles's law, V1 over T1 equals V2 over T2. And pressure and temperature are correlated in a similar law, Gay-Lussac's law, through the equation P1 over T1 equals P2 over T2. Again, for these laws, the parameters are directly proportional. If one doubles, the other must double, so they increase together. The combined gas law is essentially a combination of these three laws, giving us P1V1 over T1 equals P2V2 over T2. With any of these laws, if we were to know all of the variables except one, we could plug in what we know and solve for what we don't, thus making simple yet accurate predictions about a gaseous system undergoing a change from one state to another. We must also understand Dalton's law as it relates to partial pressures. In a mixture of gases, each component of the mixture will exert a partial pressure, meaning the particles of that gas are responsible for some fraction of the total pressure. The partial pressure will be proportional to the mole fraction of that gas, meaning whatever the fraction of the total moles that are represented by that gas, that same proportion of the total pressure will be its partial pressure. In other words, if there was a mole of different gas particles which exert 1 atmosphere of pressure, and 0.25 moles of them are gas X, the mole fraction of X is 0.25, and it has a partial pressure of 0.25 atmospheres. The sum of the partial pressures of all the gases in a mixture must equal the total pressure. There is one more similar law called Avogadro's law, which will allow us to understand something called the molar gas volume. Avogadro's law was first expressed as a hypothesis which said that equal volumes of different gases under that same temperature and pressure must contain the same number of moles of gaseous particles. In other words, ideal gases occupy the same amount of volume regardless of their identity. Here we see equal volumes of helium, ammonia, and oxygen, and to illustrate the relationship, we clearly see the same number of particles of each. The masses are different, as each substance has a different mass, but the number of particles is identical. Over time, this hypothesis was corroborated by much data, and it became Avogadro's law, which can be expressed as V1 over N1 equals V2 over N2, meaning that volume and moles are proportional at constant temperature and pressure. This is because, given some sample of gas, if we were to increase the volume of the container that gas was in, if temperature remained constant, meaning the particles move at the same speed, the only way to maintain the same pressure or frequency of collisions with the sides of the container would be to add more gas particles. With Avogadro's law understood, there is a useful assumption we can make about ideal gases. Since we make the assumption that all ideal gases will behave the same way, regardless of the identity of the gas, we can also say something about the volume occupied by 1 mole of any ideal gas at standard temperature and pressure. As it happens, 1 mole of any ideal gas at 0 Celsius and 1 atmosphere, or STP, will occupy precisely 22.4 liters. It doesn't matter if it's oxygen, nitrogen, hydrogen, argon, or any other ideal gas. This is the molar gas volume at STP. At higher temperatures, this value would be larger, and at lower temperatures, this value would be smaller, as we know from Charles's law. If the exterior pressure were different, this would also have an effect on the volume, as we can assume based on Boyle's law. But the volume will typically be the same regardless of the identity of the gas. This has a wide range of applications, mainly that it makes calculations regarding moles and volume quite simple. If we want to find out the volume occupied by 2 moles of oxygen at STP, we can just do dimensional analysis. 2 moles times 22.4 liters per mole gives us 44.8 liters. We can convert volumes of ideal gas into molar values precisely the same way. Just bear in mind that this only works at STP. Now, the laws we just learned about illustrate the relationship between pairs of variables for a sample of gas moving from one state to another, but these can be combined to give a relationship between all of these variables, and that's the ideal gas law. This is defined by the equation PV equals nRT, where pressure, volume, moles, and temperature are all listed, and R is the ideal gas constant. This gas constant will contain the units necessary to cancel out the respective units on these other variables in order to correlate them all appropriately, and there are several different forms of R that are comprised of the different common units we will often use for these parameters. Gases that show this relationship between these variables are ideal gases, which are gases that fit the assumptions of kinetic molecular theory, and this equation works quite well for gases at relatively low pressure and relatively high temperature. The ideal gas law is useful when all of the parameters for a sample of gas are known except one. Rather than the other laws we've learned, where we tend to make predictions about the change in one variable that accompanies the change in another variable, we can look at an ideal gas in an isolated state and calculate any parameter for that gas. We simply need to know the other 3 quantities. Now we have an understanding of ideal gases, which requires certain assumptions, but we will also have to know some things about non-ideal gases, or real gases. So let's make sure we understand this distinction and can describe the differences between them. First, let's recall two of the postulates of kinetic molecular theory. With ideal gases, we assume that the particles are dimensionless points, but in reality, they are not. Atoms and molecules do occupy a measurable volume, even if it's very small. We also assume that they do not interact with each other when they collide, making only totally elastic collisions. Again, this is not true. If gas particles collide, they can participate in some kind of electrostatic interaction, even if only very briefly. We make these assumptions because these two parameters are completely negligible at atmospheric pressure, where we do most of our chemistry. But there are situations where they are no longer negligible, and when that is the case, we can no longer make those assumptions, as we are dealing with a non-ideal gas. An ideal gas must be very sparse, or have a very large volume in comparison to the volume occupied by the gas particles. If this is the case, we can indeed ignore the volume of the particles and treat them as points. But if a gas is compressed until the particles are very close to one another, occupying a reasonable fraction of the total volume, then it becomes less and less feasible to ignore the volume of the particles. This means that if the pressure increases enough, the ideal gas laws do not hold. Also, in addition to having its particles spread far apart, an ideal gas has its particles moving with high velocities, such that if they happen to fly past each other, they have very little chance to interact. But if the gas is compressed and if the temperature is decreased until the particles are moving very slowly, when they pass by one another, there will be much more of a chance for a dispersion interaction or dipole-dipole interaction if they are polar. This means that if the temperature decreases enough, the ideal gas laws again do not hold. So high pressures and low temperatures cause a gas to deviate from ideal gas behavior. Although it is more difficult to describe non-ideal gas behavior in a quantitative way, we can still do so by using the van der Waals equation. This equation is set up just like the ideal gas law, PV equals nRT, but it includes two correction factors. First, we adjust the pressure term with a correction factor associated with the attraction between the particles of a gas. So instead of P, we get the quantity P plus AN squared over V squared. A is a constant that corresponds to the strength of the attraction between gas particles, which depends on their identity, as larger and more polar molecules will exhibit stronger attractions than smaller and less polar ones. And of course, N and V are moles and volume. Then we will adjust the volume term with a correction factor associated with the volume occupied by the gas particles themselves. So instead of V, we get the quantity V minus NB. B is a constant that corresponds to the size of the gas particles, which will also depend on the identity of the gas. And again, N is moles. The right side of the equation will remain unchanged. Each gas will have its own values for the constants A and B, and we will simply look them up in order to do calculations. Let's make sure to note that the van der Waals equation will reduce to the ideal gas law under ideal gas conditions. If the volume is very large and the number of moles is very small, which results in a gas that is very sparse, this would allow for the assumptions associated with ideal gases to be valid, and these correction terms will approach zero, making them negligible.
With solids and gases covered, let's look at liquids, and in particular, homogeneous mixtures in the liquid phase, which we can call solutions.
Many substances, when placed in some solvent, will dissolve, yielding a solution. In a solution, there is a solute, which is the thing that has dissolved, and a solvent, the thing that the other thing was dissolved in. And the solvent is typically present in a much greater amount. If this solvent is water, then we would call this an aqueous solution, from the Latin word for water, aqua. So any solute that dissolves in water will produce an aqueous solution. These solutes can be of different varieties. They might be covalent, like sucrose, which is table sugar. These are all neutral atoms connected by covalent bonds. If this substance dissolves, the molecules that used to be packed tightly together in a lattice will now be spread out in solution amongst the water molecules. No change has occurred to any individual molecule. The molecules are simply rearranged in space. That means that a phase change has occurred. Specifically, sucrose has gone from the solid phase to the aqueous phase. We can denote this in an equation like this one, where the S stands for solid and the AQ stands for aqueous. If we were to read this, we would understand that solid sucrose has been dissolved in water, as that is what this phase change represents. Ionic compounds like sodium chloride, which we know as table salt, can also generate aqueous solutions, but unlike covalent compounds, instead of simply dissolving, we can also say that there is complete dissociation of the ions, so that each individual ion will be solvated by water molecules, like we see here, rather than sodium and chloride ions remaining bound to each other. When this is the case, we can again display this in an equation, only this time we show solid sodium chloride generating an aqueous solution containing sodium ions and chloride ions, which we list separately, each of which are marked aqueous. Some ionic solids will not be water-soluble, so they will not form aqueous solutions. If placed in water, they would simply sit at the bottom and not dissolve. And there are many hydrophobic or nonpolar substances that also will not form an aqueous solution. Any kind of oil will behave this way, as we can see if we were to combine water and olive oil. We can see the distinctly separate layers, which means a solution is not achieved. Here, unlike something like sucrose, which can dissolve because it can then make strong interactions with water molecules, oil does not do that because it is unable to make such interactions. In general, if a substance can dissolve in another substance, we say it is miscible or soluble. If not, it is immiscible or insoluble. So when we hear the word aqueous as it pertains to a solution, we must understand that this means a solution where water is the solvent, as opposed to ether or hexanes or any other common solvent. And when we see the phase symbol AQ following any substance in a chemical equation, it means that the substance is completely dissolved in water, making it by definition an aqueous solution. Water itself in the liquid form will simply have the phase symbol L for liquid, rather than aqueous, because it is a pure liquid and it doesn't make sense to imply that water is dissolved within itself. Now that we know what a solution is, we need to be able to describe concentration so that we know how much of something is found in solution. The way we will do that is by using molarity, which is symbolized by a capital M. This refers to the moles of a particular solute that are present per liter of solution. We should be able to calculate the molarity of any substance given the moles of that substance and the total volume of the solution. For example, let's say that a 355 milliliter soft drink contains 0.133 moles of sucrose, or table sugar. What is the molar concentration of sugar in the soft drink? Well, as we said, molarity is defined as moles solute per liter of solution, so let's plug the numbers in. 0.133 moles goes on the top because that's how much solute we have. And as for the volume of the solution, this must be in liters. So let's convert our 355 milliliters into 0.355 liters and put that on the bottom. Doing the math, we should get 0.375 molar as the concentration of sugar in the drink. This kind of information is useful because we could then calculate the amount of sugar that would be in any volume of the soft drink, or the volume of soft drink that would be required to provide a particular amount of sugar. We can say that solutions with a high concentration are concentrated, and those with a low concentration are dilute.
Now that we understand what solutions are, we want to learn about how we can separate the components of a solution. The two techniques we will want to be familiar with are called chromatography and distillation.
Chromatography is a way of separating components of a mixture by virtue of differing polarity. When performing paper chromatography, the paper is called the stationary phase, and a solvent is used, which is called the mobile phase. A sample is loaded onto the paper towards the bottom, and solvent is allowed to rise up the paper, taking the mixture along with it. As the mixture moves up the paper, its components will begin to separate on the basis of how well they form intermolecular interactions with the stationary phase versus the mobile phase. Compounds that are more polar will be able to interact with the polar components of the paper, and these electrostatic interactions will cause them to slow down, and they won't travel up the paper as far. Compounds that are less polar will not interact well with the paper and will instead get pushed along with the mobile phase and will thus travel farther up the paper. So when looking at such a chromatogram, we can see the separation of a mixture into its components, with the one that traveled the least distance being the most polar compound, and with polarity decreasing going up, with the one that traveled the farthest being the least polar. Thin layer chromatography is very similar. It simply uses a plate with a silicate material on it rather than paper, and this also makes strong interactions with polar compounds. Column chromatography is yet another technique that works by the same principles, but it is useful for separating mixtures in larger amounts. Here, the stationary phase is a silica gel instead of paper, and the mobile phase will travel down the column, pushing the components along with it at differing rates, depending on how polar they are, and how well they interact with the polar stationary phase. Distillation is another separation technique, though it separates components of a mixture on the basis of differing boiling points. We know that the stronger the intermolecular forces, the higher a substance will boil, as those interactions must cease in order for vaporization to occur. So a mixture is heated until it is at a temperature that is above the boiling point of one component, but below the boiling point of the other. This way, one component vaporizes and the other does not. The one that turns to vapor will travel upwards and then enter a condenser, which is a very cool environment, so that it can condense, returning to the liquid phase, where it is collected in a receiving flask. This is a simple way to separate the components of a liquid solution.
With so much understood about solutions, let's now pivot a bit and talk about things like spectroscopy and the electromagnetic spectrum.
We can get a lot of information about matter by seeing how it interacts with light. Light is able to cause excitations in matter of a few different varieties, causing molecules to rotate, bend, or vibrate. Different frequencies of light induce different things, so let's look at the electromagnetic spectrum to get a sense of these different types of frequencies. Light with the shortest wavelength and therefore highest frequency is gamma rays. From there we have X-rays, ultraviolet or UV rays, visible light, infrared, microwaves, and radio waves. Microwave radiation is associated with transitions in molecular rotational levels. Absorbing and releasing photons of these energies changes the way that molecules rotate. Infrared radiation is associated with transitions in molecular vibrational levels. Absorbing and releasing photons of these energies changes the way that molecules vibrate. And ultraviolet as well as visible light is associated with transitions in electronic energy levels. So when an electron within an atom absorbs a photon of a certain energy, it will jump up to a higher energy level or greater N value. It can then emit a photon of a characteristic energy and relax back down to a lower energy. This is how we see things with our eyes, by sensing the photons emitted by atoms within objects, when their electrons move down to a lower energy level after being excited. During such events, the change in energy of the electron is precisely equal to the energy of the photon. The energy of the photon is given by this equation, where it will be equal to something called Planck's constant times the frequency. And the frequency is related to the wavelength of light by this equation, where the speed of light, given by c, is equal to lambda, the wavelength, times nu, the frequency. It may be confusing to think of light as both a particle called a photon and a wave with a wavelength and frequency at the same time, but this is a ramification of wave-particle duality, which is a central theme of quantum physics. We should also note that the wavelength of light that is produced by an object is temperature dependent. If we look at something called a black body, which emits light of all wavelengths, the maximum emission wavelength, or the most commonly emitted wavelength of light, will shift towards lower wavelengths and higher energies as the temperature of an object increases. If sufficiently hot, this wavelength enters the range of visible light, which is why very hot things glow. Finally, we can apply this concept to solutions by looking at the Beer-Lambert Law. This relates the intensity of molecular absorbance to the molecular concentration. This essentially means that the more concentrated a solution, the more efficiently it will absorb light of a particular wavelength, often in the UV range. A stands for absorbance and will be between 0 and 1. 1 means all the light is absorbed, 0 means none is absorbed. This epsilon stands for molar absorptivity, measured in molar per centimeter, so it describes how intensely a sample absorbs light of a specific wavelength. B is the path length, or the distance light is traveling through the sample, and C is the concentration of the solution. This relationship can be used to study rates of reaction, which we will get to in another unit.
So that wraps up Unit 3. I'll see you over in Unit 4, where we will examine chemical reactions.